So good morning, everyone. Welcome to the second day of MFPS. It's my great pleasure to introduce Robert Atkey, who's going to talk to us about polynomial time and dependent types.
Okay. So just before I do that, I'd just like to advertise this summer school that we're running in Strathclyde. It's part of the series of the Scottish Programming Languages and Verification Summer Schools. This is the 5th edition. It's in sunny Glasgow, as you can see here. This is what Glasgow looks like. It's Glasgow green. It will actually be, I think, where is it? That's the building I work in. It'll be there. It's nice inside. So these are the speakers. So we've got Lindsay Cooper about distributed systems, core courses on category theory and type theory, and then some other specialized courses by some good people. And we have an SPLS, or Scottish Programming Languages Seminar Zulip. So there's a public stream on there. But also here's the website. So it's quite reasonably priced for PhD students and for industry people as well. So please either come or send your PhD students. Okay. So what I'm actually going to talk about is some work I've done on trying to combine implicit computational complexity. So that's sort of making programming languages where you can only write programs of limited complexity with dependent types, and seeing how far, trying to see how far we can get with sort of doing some computational complexity theory, but without ever worrying, not even just not worrying about Turing machines and low-level models of computation, but even worrying about steps and actually counting things in too much. So one motivation for this is that dependent type theory is quite popular now to think of it as maybe a programming language, and maybe even like one day industrial programmers will start writing programs with dependent types. And this sort of already happens with things like TypeScript. There are sort of little bits of dependent types in there. And the nice thing is it's also a proof language. So we can write programs and we can reason about them, but we can only really reason about the programs we write in the theory, reason about their extensional behavior. So it's like, if we put this in, then something that looks like this will come out the other end. But what if you want to talk about those programs' complexity? So we can try to do some kind of embedding of another programming language inside this big system, and then we can reason about complexity by putting in a cost model. But if you want to use the type theory itself as the programming language, and then say something like, this won't run too long, or this will have a reasonable complexity, then we can't actually do that at the moment. There's no way of talking about the program's complexity themselves. And there's quite a lot of sort of big design space here, and I'm just going to pick part of it. So one is, are the costs extrinsic or intrinsic? So there's been quite a few works where the programmer is expected to add some kind of tick effect that happens, and then afterwards you then prove something about how many ticks occurred during the execution. And this is nice because then you can control what it is you expect to be the expensive operation. Is it the number of comparisons for a sorting algorithm or something? But if we're doing complexity theory, we need to sort of have some kind of intrinsic resource, right? That's actually has something to do with the thing that's being computed. The other thing is explicit or implicit accounting. So for some purposes, we might actually need to know that this program takes, on average, maybe this number of steps. But sometimes we just want to know this program is polytime for all inputs if we just want to restrict to certain complexity classes. So in this work, I'm going to talk about making it polytime for all inputs, and we'll see how we can use that as well. And then the crucial part for dependent types is how to mediate between the intentional reasoning about the program, which sort of makes fewer things equal, and the extensional meaning. So how do we stop the costs interfering with the behavior? So one nice answer to that is this cost-counted logical framework, where they use a sort of nice phase separation style thing to make sure that you can program with costs and then erase them afterwards when you want to actually do some extensional reasoning. And I'm going to show another way here, which depends on linear types. So I'll get to that. Okay, so what the plan is implicit polynomial time by linear typing combined with extensional program reasoning with dependent types. And a kind of goal, maybe, is some kind of synthetic computational complexity theory. So we never have to construct Turing machines or anything like that. We just program with functions. The linear typing keeps us within the complexity bounds, but we can use the extensional program reasoning to define other complexity classes on top of it. There's still a big question mark, and I'm nowhere near doing anything like this yet. So first, I'm going to show you two ways of doing implicit polynomial time using linear types. Okay, so why linear types? So here's the kind of representative rule of some kind of linear type system where if we've got a function m, it takes a's to b's, it uses resources in gamma 1. We've got an argument for it, n, which is type A, that uses the resources in gamma 2, and then the combined resources are kept separate. There's no way of sharing resources between the function and its argument. And this makes sure that really what happens is, reading upwards, we can't duplicate things. So the values in the system is going to represent the ability to spend time during computation. So in particular, we're going to treat inductive values as a kind of fuel. They're the kind of thing that allows us to iterate and pump through and get things sort of being more than just linear complexity. And we also have to disallow anything with the functional kind of values being duplicated because they can hide these inductive values inside them. We'll say it is going to be affine linear types. So discarding things is allowed. We're allowed to just sort of throw fuel away and sort of pretend that we're going to do more computation than we actually were. Okay. So I just want to sort of step back to say what is polynomial time, and then how can we build a type system to do this. So polynomial time is meant to be some axiomatization of what is feasible computation. So what does it mean to have something that's going to run in a reasonable amount of time? And I think when you look at the definition, this doesn't seem very reasonable because, okay, maybe it's n to the 1,000, and that's not going to be actually very feasible. But if you break it down, I think this is what complexity theorists like to say, is that feasible computation should be closed under, well, okay, we have to be able to iterate over the input. That seems reasonable. We should be able to do 2 iterations over the input. And if you can do 2, you can do 3, you can do 3, you can do 4. And then the slightly iffy one is that we're allowed to nest iterations. If we're allowed to iterate over the input, then we're allowed to iterate over the input while we're iterating over the input. And that's what gets us the polynomial degrees. But once we allow these, then we get sort of inevitably to polynomial time. So let's see how we could build a system for polynomial time using linear types. So obviously allowing iteration over the input is easy enough, and allowing composition, right, we're going to do this in a lambda calculus, so that works. So it's the nesting of iterations that we need to control. We need to make sure that we do only iterate over the input, but not in a way that allows us to build bigger things to then iterate over. So we're going to make sure we can only iterate over the input. So one idea is to separate iterable and non-iterable types. So I'm going to have a type of iterable natural numbers. And these are, we're allowed to sort of construct A's by iteration over them. And notice, because we're linear, in the 0 case, there's nothing in the context. And in the step case, there's the context only gets the sort of result of the rest of the iteration. This tells us take any natural number and iterate over it. So these natural numbers are going to come from the input, and they can do iteration to produce values. And then we also have this hollow natural number, this kind of natural number with a hole. And these ones are just there for representation. We can pattern match on them, and we can look at them. But in the step case here, we don't get another value of type A. So we get to see whether it's a 0 here or a successor, but we don't get to do any iteration on it. Right? So these are ones we're going to use for sort of we can explore these natural numbers. As long as we have iteration from an iterable nat, we can explore this natural number, but we can't ever iterate on it. And we can have other non-iterable types as well. So any kind of inductive type, as long as we don't iterate on it, isn't going to be a problem. We can only look at it as far as the fuel that we get from an iterable type allows. So this still wouldn't give us polynomial time, except because if we could construct these iterable types from iterable types, then we could sort of use them to multiply and then get up to exponentials. So the way we kind of stop that is basically to ban any kind of construction. So we adopt a NIMBY approach where we make sure that things that can be used to make computation go are not constructible by the program. So we're not allowed to construct any NAT values within the program. So all the NATs must come from the outside. So we never have closed programs. We always have an input of type NAT, which is going to be used by the program to drive its computation along. On the other hand, we can construct these non-iterable natural numbers in any other kind of non-iterable type. So we can use that to build our output as large as we like, but we can't construct any of the natural numbers that we can iterate on. Slightly oddly, we can duplicate these iterable natural numbers. So we're not allowed to construct new ones using successor. So actually adding 0 would be not that bad, but adding successor, we could use some of the inputs, so sort of drive that over and over again to produce larger natural numbers. But if we can just duplicate the input, this will allow us to do the nesting of iterations. And we'll see why in a second. So this system ends up being very similar to one of Neil Jones', where this is the subtitle of the paper, but life without cons. We had a first order language, which we could show was polynomial time, but then when he added higher order functions, it became exponential time. But with linear types, we stay within polynomial time here. So it's a bit difficult to see, I think, why this works immediately, but we can sort of go through a completeness proof of this system to see why it actually gets polynomial time. So it doesn't prove it's sound, but it does prove that we can at least achieve polynomial time. So if we assume that there's some non-iterable type ST, which is like the state of a Turing machine or something, so you can imagine a thing that's got the tape before and after and what's under the head, and there's an F, which simulates the one step of the Turing machine, and we've got a polynomial P of n, which we're going to try. We know that this machine will terminate in that many steps. So now we can build a term which iterates fpn times. So we can do that once here. So this takes a natural number and the initial state and gives us a final state of running f that many times. And then we can nest them with this other iterator, which will run it. It duplicates the natural number here, and then runs the kind of outer one n times, but then feeds that natural number in to run each one underneath n times. So each ikn is going to iterate f n to the k times, and then we get to add up to the whole polynomial. We can just compose things over and over again. So we can basically turn the polynomial into a great big bunch of iterators composed together, and that will run the program that many times. So that will allow us to sort of step through the Turing machine, and then we can take a Turing machine that we know to terminate in polynomial time and run it to the end. And it's allowed to sort of do single steps, like pattern matching on the state, to do one step each time. This works, and it's enough to get a system which is sort of intentionally complete for polynomial time. So in theory, you could write every polynomial time algorithm up to coding things into the state type. But it's not much fun to program in, because if you're trying to do functional programming, so the point here is that we want to make constructions easy to make, it's not much fun to actually write programs, because we only have this natural number input that tells us how big the input is in some sense. And then we have to write our program completely around how this completely around just iterating over this. So a much nicer system, due to Martin Hoffman, is this LFPL, this linear functional programming language. And the key idea here is that we have first-class iterability. So we can iterate over the input, but instead of it just sort of allowing us to do that, as we do so, it sort of yields the ability to iterate over its subparts as diamonds. So what does that mean? So we do now allow construction using diamonds. So we construct a zero, we construct a successor using diamonds. But when we iterate, we get these diamonds back. So in the zero case, we get a diamond. In the step case, we get a diamond back. And this will allow us to construct other structures from the sort of iterability of the input to build things that we can further iterate on. And the key point now is that this applies to pretty much any other kind of finitely branching inductive type. So the construction consumes diamonds. So here's the tree, the leaf consumes a diamond. Node takes two subtrees and produces a diamond. And the iterator, we just add diamonds everywhere. And in fact, like you can, in the model I'm going to show later on, you can sort of say that initial algebras exist for any kind of finite tree F, where we just append a diamond onto it as well. It gives us enough power to do the iteration. And then this one is enough, because again, with the same setup, we have some F with non-iterable types. And a polynomial. And now what happens is that it takes the natural number that we're using for the fuel, but now has to reconstruct it as it goes. So we can't duplicate them anymore because now they're kind of heavy types. So in the previous one, we could duplicate natural numbers. But here we can't duplicate them anymore because that would mean duplicating these diamonds. But here we can reconstruct the natural number as we go. So it sucks in this natural number in initial state and produces the same natural number and the final state, but it has to sort of reconstruct it as it goes. And the point of this extra work is that in the higher degree case, when we get the diamond here, we can then we also get the diamond, but we also get back the number from the sub-iteration, and then we can pass that in. So the later iteration along that row, we can pass that down into the next level here, this n here. So this doesn't give us the kind of nice rectangular shape we had before, but we get this kind of triangle shape. So we end up with the iterator INK performs n choose k iterations, but then we can compose these together in the same way again to get any polynomial we like. So it's a little bit more complicated to do the completeness proof, but because we can use any data types we like and any kind of shapes we like, we can program much more easily. Okay. I said I wasn't going to talk about explicit complexity, but the same diamond idea, using ideas of Martin Hofmann again, can be used to do explicit complexity by now just making the diamond into a kind of token that we just use to pay in advance for work done by the machine. So inspired by amortized complexity analysis, we literally store potential inside the data structures as extra values. So we reinterpret this diamond as not a kind of abstract notion of iterability that we can sort of reuse. It's a cost of a step of iteration that we have to pay every time we do one recursive call. So building a NAT still requires the diamonds, but now the iteration no longer gives you them back. So you can't nest iterations anymore. So we're literally consuming the diamonds as we do this. And so now the number of diamonds you start with is going to be linearly proportional to the actual number of steps that you're going to take during the computation. So this allows you, if you can count the diamonds, allows you to sort of say quite closely exactly how many steps this program is going to take. So indeed, one way of doing this in a simply typed system is we annotate every data structure with the number of diamonds per node. And then we do allow duplication, but now we have to separate the number of diamonds. And as was nicely shown by Hoffman and Yost, we can use linear programming to actually infer these in many cases. So that was two different ways of doing polynomial time computation. They're kind of well known. I think the The cons-free one I've never seen written out with the higher order version with linear types. And actually, the way I arrived at that was to take a model of soft affine linear logic, Yves Lefont's system, which has this bang, which only allows, instead of going bang A to bang A, tensor bang A, it goes bang A to some fixed n. And so it allows this duplication of things, but exactly the same model works for this cons-free system and gives you a much nicer, I think, sort of functional programming style. But what I want to do now is try to work out how to embed this linear discipline for keeping to polynomial time into dependent types. And the fundamental problem here, sort of crudely put, is the syntax just doesn't work out. So in type theory, we have contexts where the variables are used in two different ways. They're used in the term M, and they might be actually then used as actual pieces of data, which are going to be used for computation. But also they're used in the types to construct types, and there might even be types inside M as well, where they're kind of used logically. They're just used there for making sure that everything makes sense. And this clashes quite severely with linear logic's idea that if a variable is in the context, then it must be used. So it really is like these are the resources that you are using for the computation. And when we have them in the context where they're not being used in the computation, but they are being used in the types, it gets confusing. And then they're used twice in the types. Does that count as a use? And there's several different ways around this. But I'm going to show you a particular way that works well when we want to treat the linear typing as a kind of restriction of the programs you write. So I call this quantitative type theory, but it goes back to ideas by Colin McBride. So the idea is that there are sort of now several systems of so-called quantitative typing where we annotate the variables with usages from a semi-ring. So this sort of somehow says that we're going to use this x1, but we're recording the fact that we're using it row 1 many times, or row 1 sort of amount. So these don't necessarily numbers. They could be security levels. They could be sort of other things. And then the idea to extend this to dependent types is to treat the 0 of the semi-ring especially. So we are going to allow 0 usage data to appear in the types. So in these systems, if the row is 0, then often that means that it's unused in the term. Like this is sort of a property of the specific system. And this has nice effects just for things like the formalization of these systems, because so anyone who's tried to formalize a substructural type system knows that you get into horrible problems with shifting things around because the names don't stay stable when you're combining contexts. If you're allowed to just annotate them with whether or not they're used, then the names stay stable. You just add them together, and the whole thing becomes my student James Wood, so that you can actually use linear algebra then to talk about substitutions and so on. So it's really nice. But the other thing is that we can use 0 usage data to say that's only used in the types. And the nice thing about that is that when it combines with something else, it doesn't affect whether or not it's used in the term. So now we have judgments like this, where we have the variables are annotated with their usage, and also the result as well. And so we have the sort of theory splits into 2 halves. One where we have sigma equals 0 at the end here. And then we have a copy, basically another copy of type theory with everything annotated with zeros. And we have one where sigma equals 1. And this is sort of the real computational world. This is where the rows start to matter. And we can impose a linear typing discipline. So we split the theory into one where we don't track resources in any way whatsoever, because 0 plus 0 is 0, and 0 times something else is 0. But then we have this real computational world where the resources start to matter. And the rule which makes this all kind of work and shows that QTT is somehow a bit of a trick sometimes is this omissible zeroing rule. So whenever we have a judgment that is in the linear world, we can always erase it to one which is in the nonlinear world, and everything becomes zeroed out. So this basically means that every linear term has some kind of extensional constituent that tells you what it does. And then this is what allows us to move any kind of term that we've written in the linear language into the types. So in other systems where there's a strict separation between intuitionistic types and linear types, then in those cases, we can't make something depend on a linear term. This allows us to take a linear term and forget that it was in the restricted section and put it into the types. And this also shows that the linear system is just, at the moment, a restriction of the intuitionistic. So all we're going to do is stop people writing programs at this point. Okay. So now, how do we combine this QTT with LFPL as one example? So here's the diamond type expressed as a dependent typing rule. So we have type formation. So it says in any context, we don't need any resources to say that diamond is a type. And then the middle rule is kind of weird. What it says is that in the zero fragment, so that's in the sort of unresourced world where everything's free, then we can construct an inhabitant of the diamond type. And it's just sort of construct a star. So in the type world, diamond is going to act like the unit type. We're allowed to freely create them, throw them away, and do anything we like. But the rules will say that we're not allowed to do this in the resourced world. So we can construct diamonds for reasoning, and we can do it freely, and that will also mean that we can sort of simulate any computation we like just by paying for it with these free diamonds. But there's no constructor which works in the sigma equals 1 fragment. So we have a 1 on top of the colon. So diamonds are free for reasoning, but they're not free when we actually want to do computation. And then this other rule says that this in the zero fragment, the diamond really does act like the unit type. And then we have the rules you might imagine for combining, for making natural numbers. So to make a zero, we have to have a diamond. And then in the successor case, the diamond and the natural number have to come with separate resources, and then we add them up. And so this is actually kind of zipping the two together, just adding up these rows which are on each of the variables. So we actually zip them together. So, or adding the vector of costs. And just this last premise, just make sure they have the same types. So this makes sure that the diamond which is being used is separate from the diamonds which are contained within the natural number that we're making the successor of. And then this sort of complicated rule is the eliminator for natural numbers. And the careful thing is that it makes sure that everything that is required to make sure the types make sense is still there. But if we're not allowed to use it at runtime, or we're not allowed to use its resources, then it's annotated with a 0. So at the top, there's the inductive hypothesis, or the motive, yeah. And so this is all done with 0 resources just to construct the type. Then we've got our natural number, m. Then in the 0 case, we still need the gamma, but we 0 out its resources to make sure that we don't pass any resources through the iteration. But we do get a diamond, and then we construct the P for the 0 case. In the successor case, we get a diamond, but we get to know that there's a natural number, but we're not allowed to use this at runtime. So this is annotated with 0. So this term n is not allowed to use this natural number in any place where they actually do computation on it. So you can use it to construct types, and it's needed to construct this type here in the result, and this type here, but it's not allowed to use this. So we're restricted to using what came back from the rest of the elimination. And then this gives us p of m at the end. An important thing here is that in the types, we're allowed to construct diamonds for free. So this doesn't use this D. We're allowed to construct this diamond for free to construct the types used to state this. And also when these sigmas are all 0, then these diamonds are free and actually sort of definitionally equal to the star. So it just acts like the normal NAT iterator, except there's this extra spare unit argument flying around. Okay. So I've sort of tried to convince you it was complete, and I think that's sort of clear that sort of carries over to the dependently typed case. For soundness, I used an adaptation of a realizability technique by Ugo Dalago and Martin Hoffman. And I think this is quite nice because it reveals exactly how the resources are being sort of passed through the program in quite a complicated way. So their technique relies on something they call a resource monoid. And I think the nicest way to state this is that it's a certain kind of enriched symmetric monoidal category. So if we let n with a negative infinity be the category with objects which are natural numbers and sort of added with a negative infinity. So this is going to be number of steps available to do computation with a negative infinity if this computation isn't possible. And then the arrows are just the ordering. This is a strict symmetric monoidal category with plus and 0. And then to unfold what this says about M, so this means that there is M itself is a commutative monoid. So these M's, the things in M, are going to represent amounts of potential that can be used to make a computation run. So we can add up potential, and the kind of HOM object, if you like, is the difference between two potentials that gives us some number of steps that we can use. So the difference between alpha and alpha must be well, greater than 0, it's going to be 0 usually. But if in the general case, if we start with potential alpha and end up in potential beta, then either that yields some number of steps that we can then use to make the computation run, or if there isn't enough in alpha to get to beta, then we'll get negative infinity. And then this axiom then is the sort of composition from the enriched category structure, and then this is the symmetric monoidal one that allows us to add potentials but do a kind of framing separation logic style. So the easiest resource monoid is just natural numbers. So we have a certain amount of resource, which is a natural number, and then this differencing operation just subtracts the start one from the end one, assuming that that was possible. Have I got it the right way around? There's a wrinkle that when we put it into the realizability model in a second, this is either excessively pedantic or you have to make it count just the recursion steps, because otherwise it tries to count. There's no way of hiding, sort of padding this one. But for polynomial time, what do? We have the monoid carrier consists of pairs of a natural number, which you can think of as the amount of iterability in that thing, and a polynomial. So this reflects the fact that values in the system have two kind of properties which we're interested in. One is, do they actually contain any fuel which can be used to power an iteration? And that's recorded by the first component, the natural number. So this is, roughly speaking, how big is your data structure going to be? The second one is a polynomial, which if this piece of data is a function, then how much computation will it do when we actually apply it to something? So if we apply it to something of size n, this is the amount of computation it will do. And then for the LFPL system, we just add them for the monoid structure. And the differencing well, we make sure that the potential at the end is at least as big as the potential we start with for the size, but then we subtract the polynomials at the larger size, assuming that we have enough resource to do that. So that gives us the easiest way to see this work is when one of them is 0, then we can see that this just gives us the polynomial. If we start with 0, go to here, we get the right size. And then for the cons-free system, all we have to do is change the plus here to a maximum. And that's what gives us the duplication behavior. Because now, for a natural number, the polynomial part is going to be 0. And when we can duplicate, and we just take the maximum over the two. So for the soundness, I'm just going to assume there's some model of computation with the cost model. So this is a call by value untyped lambda calculus that takes expressions and an environment, and then within k steps evaluates to a value v. And then, okay, this is not as bad as it looks. So what's a type going to be interpreted as? This is a simplification. So types, they're going to be some carrier, which is the set of extensional values. Then there's a realizability relation that says that this element of the resource monoid and this value realize this this extensional value. And this is not like assembly, so we're not going to make sure that everything is realizable. This is quite important to how the system works. And then I said function, this should be a term. So a term is going to be realized by some function which tells you what the extensional behavior is, such that there exists an expression which implements that term, and then a potential in this sub-resource monoid for the program term. So this is there's going to be a sub-resource monoid, which is only for top-level terms, which in terms of the polynomial type ones, we're allowed to have a polynomial because that's the polynomial of the program of how many steps the program will take. But a top-level program cannot contain a natural number itself. So there's no natural number constants allowed within the program, nothing of size in the program. And if there were, this would allow us to sort of break. This would give us a free resource that we could duplicate without control. And then, right, so given this is the fixed part for the program, such that for any potential that comes from the input and it's realizing value and the actual x, if that potential and the value realizes x, then there exists a final potential and a number of steps and a final value. So the evaluation works within k steps. The final value is a realizer for the extensional value. And the difference between the potential that comes from the input and the potential from the program itself, when we want beta left at the end for the potential for the output, is greater than the number of steps taken by the program. So this difference between the two potentials is big enough to pay for the number of steps. This isn't quite enough to make it work for iteration. So just with that, we only get, we can only write or construct programs which are going to be linear time. So for iteration, we need a little bit more extra structure on these resource monoids. So we need something which, given a size, gives us potential for that size of data. So this is going to sort of put something in that first component. Something that tells us that we can raise the degree of potential and a scaling operation that scales something for a fixed number of iterations. And the key property is that if we've raised the potential, so we've increased its degree, then as long as the size of the potential is greater than n, then that can pay for n many iterations and retain the size. This sort of shows that if we raise the degree of the polynomial, then it's always going to beat just having a fixed number of iterations of that polynomial for any n, as long as the potential in the size is n. Okay, and then in the end, the simplified soundness is if we have one natural number input and we create a natural number output, then there must be a realizer which produces this, which runs this in polynomial time in the size of this input. So it's a very kind of type-directed sort of notion of how big the input is. So we have to be wary. If the type here is more complex, then we have to know how that's accounting for the sizes. Okay, here's some denotations of types. So yeah, in the explicit amortized system, then we're just counting with natural numbers for the resources. So a diamond, we must have at least one resource to pay for it. But with LFPL, the diamond, we now have a natural number and a polynomial, and so we must have at least one diamond to pay for it. But for the natural numbers themselves, we must have enough resources to pay for at least the size of the natural number. Okay, so that's enough to prove that within this system, if you write something in the sigma equals 1 fragment, then we get a polynomial time realizer. So this is sort of interesting, but it only works outside the calculus, right? You write these programs, and then the sort of external system can see that they're a polynomial time, and the programmer can be happy that they've written something in polynomial time, and it's like feasible and everything. But how do we kind of reflect back on this back into the calculus? So we can add a type constructor, R, I call it for realizability here, which restricts a type to its realizable elements. So if we write a term M in the sigma equals 1 fragment, and it's closed as far as resources are concerned, so it's allowed to have computational, logical things it depends on, then we can, then it's an inhabitant of this Rm, of Ra. So it's saying that this is one of the elements of A which is realizable. So in particular, if A is nat arrow nat, then this Ra is going to say this is the polynomial time functions from nat to nat. And then we can always reverse this in any fragment of the calculus to get back out the function, get back out the value. And we know that it's going to be realizable. So this sigma prime here could be 1 or it could be 0. So once we have this, then the tantalizing thing is that we can start to talk about different complexity things within the calculus. So let's define a decision problem as a kind of pair. So U here is the universe type, so set. So we have a set of instances, and then some predicate that says whether or not this is one of the instances that we care about. So now with this R constructor, we can define polynomial time on decision problems, or polynomial time decision problems, as a type within the calculus. So we just say that there exists an F, which is a realizable function from A to bool. So this is going to be some polynomial time function from A to bool, such that, and then there's a correctness criterion here. So for all A's, when we sort of unrealize F, then apply it to A, if that's true, if and only if this PA is inhabited. Then go a bit further, and we can do polynomial time reductions between problems. So we've got problem AP, we can reduce it to BQ if there's a thing which maps A's to B's in polytime, such that solutions to the mapped version, if and only if there are solutions to the unmapped version. And these do look very similar to kind of polynomial functors or containers, right? So this is sort of shapes and positions, and these would be the Cartesian morphisms of containers. So it's a bit like problem reductions or sort of question-answer pairs. Okay, so that's not so surprising that we can do polynomial time within the system. But once we start adding effects, we can get sort of further complexity classes. So if we have this simple sort of decision tree data type, so we have a return and a choice. And here, this Boolean function basically gives us the equivalent of linear logic's with product. So we have to, when someone uses this in a linear context, they have to choose whether they're doing true or false. And once they apply it, they don't get it back anymore. So these are going to be trees where, in a linear context, only one path can be taken through the tree. And we can also define in the zero fragment something which runs one of these things. We give it a list of Booleans and one of these choice trees, and then we maybe get an A, because we might not get an A because we might run out of Booleans to make choices with. And then we can define the MP class by, we now need a realizer. So this is still the same decision problem format. But now we have a realizer which takes A's and gives us choice trees that end in Booleans, such that for all inputs, this bracket runs all the way to here. So it's in the good set if there exists a witness such that when we run the realizer with the witness, then it returns true. So we can now sort of use this fact that we can express polynomial time to express non-deterministic polynomial time by writing it as something with a something which produces extra data. Yeah, it's extra data of the choice tree. Another step is to sort of go for a probabilistic sort of effect. So now instead of sort of choice trees, we have choice trees annotated with something at interval 0 to 1. So again, we use this Boolean to choose which subtree to go into. And now we can sort of define a probability that this dist over a bool is going to be true. So it just adds up all the leaves which, well, the probabilities of all the leaves which end in true. And then we can define something like the BPP class. So this is bounded error probability. So this says that there is a realizer which, given an F, so the realizer F, which given an A, produces a distribution over the Booleans, such that for any instance, the probability that it returns true is greater than 2/3 if it's in the class. This is it's allowed to be wrong sometimes for different choices, but it must be right 2/3 of the time. And so this is the BPP class. Or is it? So my understanding is that the definition of BPP depends on the meta theory you're talking about. And so P and NP are kind of stable under this because they're sort of syntactically defined classes. This one, it depends on what you can use to prove this statement to actually sort of work out what the class is. This is BPP relative to type theory. Okay, this is the end. So I've shown you possibly some way to kind of doing complexity theory within type theory by using the dependent type theory to do the semantic parts, like what is a problem, how do we solve problems, and how do we reason about them, and then linear types to actually control the complexity. So I've given two systems, this cons free one and the MFPL one, and I claim it's a kind of smooth combination of dependent type theory and implicit computational complexity. So there's other ways of doing this. This is a relatively smooth one. And I think the nice thing is these synthetic definitions of different complexity classes. And just to say that the soundless proof has been formalized in Agda, which was a great help. And that's where this idea of the resource monoids being in rich categories came from, because that turned out to be much easier than reasoning about monoids directly. Because then you can think of you imagine each of these steps in the proof is building up a great big term, which is quite complicated, and then you have to reason about all the steps as they go through, but it's actually done by composing arrows in this, or arrow-like things in this resource monoid. It turned out to be much easier that way. So what would I like to do next? So it's quite clear, I think, how to get different more complexity classes, so things like co-NP and p-space. So p-space you could do in terms of the alternating for all and exists characterization. I think it's possible to write complexity classes which rely on polytime circuit generators. So you get an instance of the problem, and then there's a polytime program which generates a circuit which then solves that one. So in some sense, these are all just sort of simple matters of programming. So polytype circuit generators, if you've got a notion of circuit, and then you can write an interpreter for it that doesn't need to be itself complexity restricted, then you just need to make sure that you can write the circuit generators in polytype. And then the crucial point, I mean, to get anywhere near any kind of complexity theory is what's needed to do any kind of completeness results, like SAT being NP complete. And now it's sort of that's where it gets difficult, because we've got this R type constructor which says, okay, this thing's implementable in restricted complexity, but the only thing that we can do with it is get the thing back out and apply it to something. So I think what's needed is something like the sort of Church-Turing axiom that's added to various realizability synthetic computability theories, which says that if we have a function, then there is a code for the Turing machine which realizes this function, and that's within the system. But here it gets more complex, because what are going to be the codes for p-time functions that is nice and easy to reason about within the system? So I'm assuming there's something like, so one answer would be the actual realizers which are used in that soundness proof. That seems a bit rough, but maybe kind of p-size circuits or something which come out, and you can actually use those to reason about, because all of these completeness proofs rely on somehow you get the source code of the thing which is used to solve it, and you use that to build an instance of another problem. So you get the source code of the Turing machine, and then use that to build a 3-SAT instance. So that's where I'm sort of looking at the moment. I think there might be applications to formalized cryptography. So in cryptography, the soundness proofs rely on the power of the attacker being less than a probabilistic time Turing machine. But as far as I'm aware, most formalized cryptographic things just axiomatize that, or stick to really simple sort of composability. Like if you've got two of them, then we compose them end to end. But here we can actually say this is polynomial time, and it works, and quantify overall polynomial time attackers. And also, a bit more practically, the explicit system with dependent type. So now we can actually say I have n many diamonds, where this n is some arbitrary term, and then actually reason about the number of diamonds which are available to the program to have a fully explicit version of the implicit, or the inferred ones of Martin Hoffman and Jan Hoffman. And that's all I've got to say. Thank you. Yeah, I don't fully understand it. So I think the problem is that apparently you can define P and NP in a way that's sort of independent of the meta theory thing, but you can't with BPP. There's something about or at least no one knows how to. Is my understanding. It's relative to what you can use to prove that statement. Yeah. I don't really understand the issue. I was told this is wrong at some time. No. So here?
Yes. So you cannot have x1.
Oh, no. So the point is that because this is heavy ring, you add up different ways it's being used. Yes, so that's the way that's solved here is that you have this plus operation, which so this premise here makes sure that they're both the same length and have the same types, but they might differ in their rows. And then this plus operation sort of pointwise adds the rows together. So that's why it works well using linear algebra ideas, because this is like vector addition, and then the scaling works. Yeah. Yeah, so that, in that one, it's the join of the each, whichever way up you go. Yeah. Yes, I think. Yes, there's a number of things that you would hope would work that don't, because they're not semi-rings. But yeah, some of these things do work. Yeah. If you're interested in that, I'd look at the Granule language from Dominic Orchard, because they've got an implemented sort of basically Haskell plus these, and they've got security levels as an explicit.
We have another question over here.
I was curious. You said this would be formalized in Okta.
Yeah.
I've been playing with something very similar in Prolog. What are the characteristics of a language that would be necessary to be able to implement something like this? Like, can you do this in Haskell? Can you do it in Algebra, Julia? Are you aware of any limits?
Do you mean implement the meta theory or implement the language itself?
Basically, independent.
The dependent part. So there is an implementation of quantitative type theory in the Idris system. It's very similar to Agda, except it also has the quantities added. So doing it with imperative systems is going to be harder. And there are implicit computational complexity systems that do work for imperative programming languages. So this one at least depends quite heavily on the fact that you have iterators as your only way of doing loops. If you've just got while loops or for loops or any kind of unstructured loops, or like not unstructured, but not necessarily bounded loops, then you're basically going to end up doing program logic style reasoning to reason about the termination of those loops and how quickly they do it. Unless you change the loops to all be for each loops over containers of known, or not statically fixed size, but known size before the loop starts. Yeah.
Yeah, this might sound very stupid, but I'm aware of these things, this kind of field of work or this simple format, but where you can kind of define how to attributes differently that correspond to some linear type lambda characters. Is there any, does that connection extend to a kind of dependent type setting in any way? You kind of say that realizable functions in some way have a corresponding format or vector?
I don't know. Yeah, I don't know much about implicit computations. Yeah. Yeah.
I mean, I have a very mean question for you too. You might send me back to Ubu and Martin Hoffman, because one of the things that when you're trying to do the semantics of this stuff, you do realizability, right? But if you're kind of being more naive-minded, you might say, where's my natural numbers object? And the question, and there is a categorical no-go result there, which says that if you try to do a dependent, or not a dependent, a linear number, a linear no, you end up with an intuitionistic one.
Yeah.
So the question I have is, what you're doing is kind of putting together these two systems where where the zero is kind of both a zero from natural numbers and then this diamond from Jake, right? And so what I wanted to know is, have you thought about kind of trying to pick up two different natural number objects and kind of making one that works for your system?
I don't know if there's an answer, but a bit. So as I said, you can make the LFPL model into an isosymmetric monoidal closed category. And in that category, then if you've got, so there's going to be a class of functors where they have initial algebras. If you add a diamond, there's a diamond tensor F blank is going to have initial algebras. So you can do that for natural numbers. I think you'd have a functor which kind of does this zeroing operation essentially and erases, and that should then take that initial algebra to the natural numbers object, I think, and then you might be able to get something out of that.
Writing it down.
Yeah, I mean that's sort of implicitly what's happening here. In the model, there's a functor which does the zeroing, which forgets the linear structure.
I'd like to
Yeah,
see
okay.
that.
Yeah, I think there's a more categorical way of stating what's good. Yeah.
One more question actually on that. Would it be correct to think of types in this context as categories?
I don't think so. There's no higher structure to them.
Right, no structure. Fair enough.
So the weird thing here is that types do contain resource specifications. So it's possible to have two types which would be equal, except they use resource-based. The way they explain resources is different. So in particular, the NAT and the NAT with a whole are extensionally, they both contain just natural numbers, but they have different resource behavior. So this makes QTT a little odd to program in sometimes because it looks like you're writing the same thing twice because it's got technically different types.
Could you implement that though? I mean, could you say that the types were categories?
Yeah.